On June 23, 1993, a mathematician named Andrew Wiles announced to the entire mathematical community that he had just solved one of the most famous and most difficult problems of the time. It had been unsolved for over 3.5 centuries, and hundreds of mathematicians, some of the greatest of all time, had all tried and failed. The problem itself was very simple. It just asks if this formula, a to the n plus b to the n equals c to the n, had any positive integer solutions for n greater than 2. In the 17th century, a mathematician named Pierre de Fermat had conjectured that there were no such solutions, and claimed that he had discovered a truly marvelous demonstration of his proposition, which the margins of his book were too narrow to contain. He never wrote down his demonstration, and the problem lived on as Fermat's last conjecture. Now, in front of the whole world, Wiles had announced that he was ready to turn this conjecture into a theorem. But a worthy problem always fights back, and Wiles was about to have a hell of a fight. But to talk about Fermat, we have to go a bit earlier in history, 2,500 years ago in ancient Greece, to a man named Pythagoras. Contrary to popular belief, Pythagoras likely wasn't the first to actually discover the Pythagorean theorem. There is evidence that the Mesopotamians knew of this theorem a millennia before Pythagoras, and only in the times of Euclid, some 2 centuries after Pythagoras, is a formal proof of the theorem given. Pythagoras himself is thought to have lived in the late 6th century BC in Greece, but there are a lot of doubts about the specifics of his life. But from what we can gather, he was certainly an eccentric figure. He had a group of followers called the Pythagoreans, who followed his strict teachings and lifestyle. There's even a story of a man named Hippasus, a follower of Pythagoras, who allegedly discovered irrational numbers and revealed this knowledge to the public. The Pythagoreans supposedly drowned him for breaking their oath of secrecy. But despite the somewhat unclear history and dubious claims that are attributed to his name, one thing is certain. His philosophy regarding mathematics, of the connection between numbers and reality, left a lasting legacy that spread throughout Greece and the West. But let's quickly take a look at what the Pythagorean theorem says. The theorem relates the sides of a right triangle. The longest side here is called the hypotenuse, let's say with length c, and the 2 shorter sides are called the legs, with lengths a and b. Then the Pythagorean theorem says that a squared plus b squared equals c squared. The fact that this is true for any right triangle makes it a powerful and useful tool in geometry. Now, the Pythagorean theorem's equation belongs to a class of equations called Diophantine equations. Diophantine equations are equations with 2 or more unknowns in which the solutions must be integers. So x squared plus y squared equals z squared is a Diophantine equation with unknowns x, y, and z. And the integer solutions of this particular equation are called Pythagorean triples. If we change the exponent to be any number n, well, it's still a Diophantine equation. These equations are named after the mathematician Diophantus, who wrote the book Arithmetica, which will be important later. Not much is known about his life except that he lived in Greece around the 3rd century, but nonetheless, Diophantine equations are a big part of mathematics even to this day. And as simple as these equations look, it turns out that many are extremely difficult to solve. Pierre de Fermat was born in 1607 in Beaumont-de-Lomagne, France. Despite his name being quite famous in mathematics, he was actually a judge by trade. He studied civil law at the University of Orleans, and only after his university studies did Fermat begin seriously doing mathematical research. He relied on a copy of Diophantus's Arithmetica, which presented Fermat with centuries of Greek mathematical thinking. He would jot down ideas in the book in sometimes incomplete scribbles, but nevertheless, the ideas and calculations that Fermat wrote on the margins of his Arithmetica showed the exemplary abilities of the French mathematician. So, what did he study? His work in analytic geometry and Introduction to Plane and Solid Loci reduced geometric problems to algebraic ones using equations. Along with his peer René Descartes, Fermat pioneered the idea of using coordinates to describe loci, or a set of points defined by some constraints. These could include lines, circles, parabolas, and so on. But the most relevant contribution from Fermat to our story is in number theory. Number theory is a vast field of mathematics, but in essence, it deals with integers like 0, 1, 2, 3, but also -1, -2, -3, and so on, and how they work with one another in equations, formulas, properties, and much more. The Diophantine equations we looked at earlier are a part of number theory. Another important subject in number theory is the nature of prime numbers, which are numbers that have no factor other than 1 and itself. They can be thought of as the building blocks of numbers, and just as understanding atoms is essential to understanding chemistry, understanding prime numbers gives us deep insight into number theory as a whole. One day, around 1637, Fermat was reading the Arithmetica when he found Diophantus's excerpt on the Pythagorean theorem. It contained a lot of observations and problems, including a large list of Pythagorean triples. In fact, there are an infinite number of Pythagorean triples, something known since antiquity. But Fermat wondered, what happens if you raise the exponent to 3, or maybe 4, or 5, or 6, or in general any positive integer n greater than 2? Will there still be positive integer triples to satisfy the equation? In the margins of his copy of Arithmetica, he wrote what he conjectured. It is impossible for a cube to be a sum of 2 cubes, a fourth power to be the sum of 2 fourth powers, or in general for any number that is a power greater than the second to be the sum of 2 like powers. He then wrote down perhaps one of the most infamous sayings in all of mathematics. I have a truly marvelous demonstration of this proposition, which this margin is too narrow to contain. He died of illness in 1665 without explaining or writing in any detail his supposed marvelous proof, unknowingly leaving the rest of the mathematical community with one of the greatest and most difficult mathematical riddles. Because Fermat was not formally a mathematician, his discoveries were not well known to the rest of the mathematical community at his time. His eldest son, Clement Samuel, collected his father's work and published Fermat's copy of the Arithmetica with all his notes, including his conjecture. Thanks to Clement Samuel, the mathematical community was able to appreciate Fermat's mathematical work. Unfortunately, much of Fermat's conjectures lacked any real proof, but eventually, over time, Fermat's conjectures turned into theorems. Except for one, Fermat's last conjecture. While Fermat may have left out his supposed proof of the full conjecture, he did leave a proof that the case n equals 4 indeed had no positive integer solutions, using a proof technique called infinite descent. This proof is a type of proof by contradiction where you assume the opposite of what you're trying to prove, then show that somewhere along the way a contradiction arises. So this means that this opposite statement cannot be true, and so the original statement must be true. So what Fermat did was that if there indeed was positive integer solutions for n equals 4, then you can always find smaller solutions. But remember, positive integers can only go so small since you can't go smaller than 1, so this infinite descent of the positive integers is not possible, a contradiction. It was quite a clever proof, but only one case out of an infinite number needed to resolve the full conjecture. But we can actually extend the case of n equals 4 to a lot more. Look at the formula a to the n plus b to the n equals c to the n. Now suppose a number d divides n, such that n equals d times m for some other integer m. So a to the dm plus b to the dm equals c to the dm. Now multiplication in the exponent is the same as power of a power, meaning this equation just turns into a to the m to the d plus b to the m to the d equals c to the m to the d. But a to the m, b to the m, and c to the m are just some arbitrary positive integers, so this is just a special case of Fermat's last theorem for the case d. So let's say we showed Fermat's last theorem for d. Then a to the m, b to the m, and c to the m cannot be positive integers, and so a, b, c cannot be positive integers. So it actually proves the case for all multiples of d. For example, let's say we wanted to prove that the case n equals 8 is true. Well, that's easy. A to the 8 plus b to the 8 equals c to the 8 can be reduced to a to the 2 times 4 plus b to the 2 times 4 equals c to the 2 times 4, which by exponent rules is a squared to the 4th plus b squared to the 4th equals c squared to the 4th. Well, this is just a case of n equals 4, which Fermat proved does not have any positive integer solutions. So by having n equals 4, we get n equals 8 for free. In general, n equals 4 gives us any multiple of 4 for free, and any case gives us all its multiples for free. But here's one useful fact about positive integers. Any positive integer is a multiple of 4, or odd primes, or both. Since we showed the case for n equals 4, if we somehow solve the case for just every odd prime, we'd solve it for every positive integer, thus proving the conjecture. Now, this seems to decrease the workload since we essentially only need to prove prime number cases, but there's an infinite number of primes. But when tackling infinity in mathematics, something is almost always bound to appear that starts toppling the problem one by one. It just happened that for Fermat's last conjecture, this process would take some time. One of the first notable mathematicians to work on Fermat's last theorem after Fermat himself is none other than the mathematical giant Leonhard Euler. Born in Switzerland in April of 1707, his father was a pastor who was adamant that his son followed in his footsteps. But Euler was gifted in mathematics from a young age, and he enrolled in the University of Basel at age 13. Fortunately for Euler, the University of Basel was home to many of the Bernoullis, a family of mathematicians. And when I mean a family of mathematicians, I mean a whole family of them. Like, look at this family tree. These are all the Bernoullis who ended up pursuing some form of mathematics. The story of the Bernoullis is a wild one, with familiar controversy, disputes, and jealousy, with incredible contributions to mathematics and science along the way. But that's a story for another time. Oh, and also get this, the Bernoulli family is directly connected to the Curie family. Yeah, that Curie. Pierre Curie, the husband of Marie Curie, is a direct descendant of jHan Bernoulli. The majority of the Bernoullis stayed mostly in Basel, and like Euler, were oftentimes pressured to pursue a career outside of mathematics, only to become mathematicians. So it's not difficult to imagine that they had a positive influence on the young talent, who, with the help of Johann I, convinced Euler's father to let him become a mathematician. And how important that was to the development of mankind. This man literally has a Wikipedia page of things named after him. And it's not in just one field or branch of mathematics. He pioneered work in number theory, complex analysis, calculus, topology, and graph theory, and even contributed to not purely mathematical fields like physics and music. He was, by all means, a once-in-a-generation talent, and he was about to challenge Fermat's last theorem. Euler wanted to further Fermat's proof of the case n equals 4 to n equals 3, using a similar argument of infinite descent. His first attempt laid a lot of groundwork to show n equals 3, but there was a gap in his proof that made it ultimately incorrect. Eventually, Euler's other work would eventually fix this gap, so Euler is credited with the first proof of n equals 3. But Euler also observed an interesting property of the equation given by Fermat's last theorem. You see, as mathematics progressed, mathematicians began to extend number systems more and more to take advantage of their useful properties. One such category of these extensions is called a ring, in which you can add, subtract, and multiply, but not necessarily divide. The idea was to look for non-integers, which we'd like to, in a sense, combine with the integers, and create a new number system which had useful properties we can take advantage of. For Euler, he looked at solutions to the equation x to the n equals 1, called nth roots of unity. Many of these roots of unities are not integers or even real numbers, but live in a realm called the complex numbers. Finding these roots involve Euler's very own Euler's formula, and by using some basic exponent rules, we can see that the nth roots of unity are of the form e to the 2 pi k over n, where k is any integer from 0 up to n minus 1. The intuition is that because these numbers are complex numbers, they can be thought of as points in 2D space. That these specific points lie at certain intervals of the unit circle such that exponentiating by n basically rotates around the circle all the way to 1. Now if we denote e to the 2i pi over n as zeta n, then the rest of the nth roots of unity are of the form zeta n to the 0, which is just 1, zeta n squared, zeta n cubed, all the way to zeta n to the n minus 1. Then for each n, we can extend the set of integers z with these nth roots of unity to get a nice ring we call z adjoin zeta n, which are all the numbers a plus b zeta n for a, b integers. We call these new number systems the cyclotomic integers. And Euler noticed that if we work in these cyclotomic integers, the equation x to the n plus y to the n can be factorized in a promising new way. Euler really didn't take this observation any further, but this idea of cyclotomic integers would return soon enough. In 1735, Euler began slowly losing sight in his right eye, and by 1766, a cataract in his left eye meant Euler would soon be completely blind. Yet the blindness did not falter his productivity, and Euler continued to pour out mathematical and scientific work. His work continued until September of 1783, when he died from a stroke. Euler left a mark on Fermat's last theorem, but it was still nowhere near solved. Other mathematicians would go on to prove other cases for different exponent values, mostly using a similar argument of infinite descent. But it was obvious that something else was needed to solve the full theorem. While looking at a case-by-case basis is not a bad method of looking for patterns and a place to start, it was time to tackle the whole problem. And the person to do it? Sophie Germain was born in April of 1776 in France. She was a woman, and in 18th century France, or really anywhere else at the time, women faced prejudice in practically every aspect of life. And academia was no different. But Germain fell in love with mathematics. At the time, France was going through a revolution, the French Revolution, if you will. The revolutionary atmosphere of the city meant she stayed at home, but Germain remained on her father's library, which helped her discover the incredible mathematical discoveries of the past. Her parents, much like Euler's, did not approve of their daughter's passion, a seemingly inappropriate subject for a woman. But nevertheless, she continued to study mathematics. In 1794, the École Polytechnique opened, a school dedicated to the highest levels of mathematical and scientific study. Unsurprisingly, women were not allowed. But Germain did not give up, obtaining lecture notes under the alias of a former student, Monsieur Antoine Auguste Leblanc. Monsieur Leblanc would receive the lecture notes and submit her work to the supervisor of the course, Joseph Louis Lagrange. Lagrange himself was a brilliant, generation-defining mathematician, and recognizing Monsieur Leblanc's brilliance, invited to meet with him. He was probably surprised to find that Monsieur Leblanc was in fact a woman, but acknowledging her talent and passion, Lagrange became Germain's mentor. Despite the odds, Germain was able to study what she loved, and her favorite subject was number theory, specifically Fermat's last conjecture. Her goal was to solve the whole thing, and to do this, she used a tool called modular arithmetic. Most of the time, arithmetic with the integers is done on a straight line, the number line. When you add or subtract, you move forward and backwards on the number line. On the other hand, modular arithmetic describes arithmetic in a circle. The most classic example of this is a clock. Let's say it currently says 10 on a standard 12-hour clock. What happens if 3 hours pass? Does the clock say 13? No, the clock circles back to 1. And we call this kind of operation the modulo operation, where the length of the clock, which here is 12, is called the modulus, such that we get 13 mod 12 is equal to 1. We can change this value to anything else. For example, the modulus can be 5. Now in this system, 3 plus 4 is not 7, but instead circles back to 2. More formulaically, if we want to calculate m mod n, we can get the residue, or remainder, of m divided by n. Now this operation is related to the system of modular arithmetic. The idea is that two numbers, a and b, are considered the same, or congruent, under some modulus n if a minus b is divisible by n. It turns out this happens if and only if a and b have the same residue. For example, 21 and 31 are congruent modulo 10 because 21 over 10 has a remainder 1, and 31 over 10 also has remainder 1. This seems simple, but the theorems and concepts based on modular arithmetic can help simplify difficult-looking problems. So what did Fermat do? Well, take any odd prime p. She looked at what she called auxiliary primes, theta, which are primes of the form 2kp plus 1 for k not divisible by 3. Then she considered a condition that theta could satisfy, called the non-consecutivity condition. This condition is satisfied if there are no two non-zero consecutive pth powers modulo theta. Now, this seems a bit complicated, but it's not too bad. You take all the non-zero integers less than theta, exponentiate them to the pth power, and make sure that none of their residues modulo theta are consecutive, that is, their difference is 1. For example, take p equals 3 and consider the auxiliary prime theta equals 2 times 1 times 3 plus 1 equals 7. Then we take every non-zero integer less than 7, so 1, 2, 3, all the way to 6. You cube each one, since our p equals 3. Then we take the residue, mod theta, and get these values. And as you can see, none of these values are consecutive, so the auxiliary prime 7 satisfies this condition. Fermat showed that once this condition is satisfied, for any solutions of a to the p plus b to the p equals c to the p, at least one of a, b, or c must be divisible by theta. So in our case, any potential solution for a cubed plus b cubed equals c cubed must have at least one of a, b, c divisible by 7. Since we found an auxiliary prime theta equals 7, that satisfies the non-consecutivity condition. But here's the key. If we can find an infinite number of these auxiliary primes satisfying this non-consecutivity condition for some prime p, this means that a to the p plus b to the p equals c to the p has no solutions. This is because if there are an infinite number of these auxiliary primes related to p, then these infinitely many primes must each divide at least one of a, b, c. This means that at least one of a, b, c must have an infinite number of factors, which is not possible. So if we can somehow verify the existence of infinitely many auxiliary primes for every odd prime p, we would solve Fermat. Unfortunately, Fermat's plan did not come to fruition. It turns out that odd primes only have a finite of these auxiliary primes which satisfy the necessary condition. For example, for p equals 3, there are only two auxiliary primes, theta equals 7 and theta equals 13, which satisfy non-consecutivity. Nevertheless, Fermat expanded upon her work on Fermat to prove some other useful statements that could whittle down various cases. The sum of her work resulted in Sophie-Germain's theorem, which, by showing an additional condition to an auxiliary prime which satisfies non-consecutivity, could prove a special case of Fermat's last theorem for the original prime. Germain's discovery directly led to the proof of the case n equals 5. The proof was fully given independently by mathematicians Lejeune Dirichlet and Adrien-Marie Legendre, who extensively used and built upon Germain's method. Legendre especially corresponded often with Germain and even presented her work to the French Academy of Sciences. Mathematician Gabriel Lame continued Germain's work to prove the case n equals 7 in 1839. While Germain's ambitions of a grand plan to solve Fermat's last theorem failed, her work left a permanent mark on the history of the problem. She exchanged letters with mathematical legend Carl Friedrich Gauss, detailing her work as Monsieur Leblanc until 1806, when due to the rising tensions of the Napoleonic Wars, Germain asked her friend General Joseph-Marie Pernety to ensure Gauss's safety. Gauss was then understandably confused when a random woman named Sophie Germain asked for his protection. When Gauss found out that Germain was Monsieur Leblanc, he wrote to her, "How can I describe my astonishment and admiration on seeing my esteemed correspondent, Monsieur Leblanc, metamorphosized into this celebrated person when a woman, because of her sex, our customs and prejudices, encounters infinitely more obstacles than men in familiarizing herself with number theory's knotty problems, yet overcomes these fetters and penetrates that which is most hidden. She doubtless has the noblest courage, extraordinary talent, and superior genius." Unfortunately, as Gauss began to move to applied mathematics, his correspondence with Germain ended, and Germain's work in mathematics ended soon after. Still, Germain would even influence work outside mathematics, most notably in the theory of elasticity. She developed breast cancer in 1829 and passed away in June of 1831 at the age of 55. Even though her grand plan had failed, she was the first mathematician to attempt Fermat in its entirety, and discovered rich theorems and concepts along the way. And she did all that while breaking societal boundaries and cemented her name in mathematical history. While Sophie Germain's ultimate plan failed, she was the first to look for a general approach to the whole problem. And soon enough, the rest of the mathematical community began to search for methods to resolve the conjecture. The French Academy of Sciences offered a series of prizes to whoever could do just that. Thus, there was a race among the brilliant minds of Paris to be the first to solve the problem. On March 1st of 1847, one such Parisian mathematician announced that he was approaching a full proof of Fermat's last theorem. His name was Gabriel Lamy, the mathematician who used Germain's methods to solve the case for n equals 7. Now, in front of the French Academy of Sciences, he declared that he could soon resolve every case, perhaps in a couple of weeks. But right after Lamy, another Parisian mathematician named Augustin Louis Cauchy also declared that he was on the verge of solving Fermat using a similar method as Lamy. Now, the race was really on. Gabriel Lamy was born in July of 1795. He entered the esteemed École Polytechnique in 1813 and then studied engineering at the École des Mines in Paris. At the time, the French Revolution and its effects on France convinced Tsar Alexander I of Russia to invite Western scientific knowledge to Russia. Thus, in 1820, Lamy was sent to St. Petersburg on behalf of France and became a professor. His time in St. Petersburg proved to be quite productive. It was also in Russia that Lamy spread Cauchy's ideas on rigorous analysis. In one incident, Lamy used Cauchy's work to criticize a proof of another professor at his institute. Unbeknownst to him, the same man whose ideas he utilized would become a fierce rival in just a few decades. In all accounts, Lamy was a respected mathematician and engineer in and out of France. The same could be said for Augustin Louis Cauchy. Born in August of 1789 in Paris to a highly ranked official, he lived through the French Revolution and the Reign of Terror as a baby. And when Napoleon Bonaparte came into power, Cauchy's father rose the ranks, and the Cauchy family formed ties with various famous mathematicians at the time, including Pierre-Simon Laplace and Joseph Louis Lagrange, who we mentioned before was a mentor of Sophie Germain. Under the influence of such mathematicians, Cauchy was bright throughout his youth and eventually was admitted to École Polytechnique in 1805 as an engineer. 2 years later, Cauchy went on to the École des Ponts et Chaussées and graduated in civil engineering, going on to work as an engineer in Cherbourg. In 1811, Lagrange gave Cauchy a mathematical problem about convex polyhedra, which Cauchy solved and published. Becoming increasingly infatuated with mathematics, Cauchy moved back to Paris in 1812 to focus on mathematical studies. In the coming years, Cauchy continued to rise the ranks of Parisian mathematics, eventually becoming a full professor at the École Polytechnique in 1816. Around the same time, 2 mathematicians in the French Academy of Sciences were dismissed due to political reasons, and one of the positions was given to Cauchy. Many in the scientific circles saw this as an outrage. In fact, Cauchy was not very popular among mathematical and scientific circles. His extreme religious beliefs and unpleasant critical nature meant he made many enemies. However, he was talented. No one could deny that. Now, these 2 brilliant minds were both standing in front of the French Academy of Sciences, claiming to be weeks away from a highly sought-after problem using the exact same methods. Weeks passed, and then months, with anticipation growing. Finally, on May 24th, the speculation and anticipation stopped as mathematician Joseph Liouville addressed the French Academy, reading a letter containing important information about the race for Fermat. But it was not from either Lamy or Cauchy. In fact, it was not from anyone in Paris or even France. The letter was from a German mathematician named Ernst Kummer, and he had found the problem in Lamy and Cauchy's method. Kummer was born in Sorau, Prussia, in January of 1810. Kummer's path into mathematics was a tragic one. Due to Napoleon's invasion of his hometown, an epidemic of typhus spread and eventually killed his father. A fierce patriot, Kummer vowed to protect his country from such invasions, and thus worked in trajectories for ballistics for the German army. This was not to diminish his influence or talent in pure mathematics in any way. In 1831, Kummer wrote a mathematical essay that awarded him a prize, which led the way to a doctorate. He went on to teach at a gymnasium in Liegnitz, Poland, an equivalent to a high school. While perhaps not as flashy, Kummer still taught and influenced future bright minds, including one Leopold Kronecker. He also continued his mathematical research, including a paper on hypergeometric series, and prominent mathematicians like Carl Jacobi and Lejeune Dirichlet realized that Kummer was destined to be more than just a schoolteacher. In 1839, Kummer was elected to the Berlin Academy of Sciences, and by 1842, with strong support from Jacobi and Dirichlet, became a professor at the University of Breslau. But what was this problem that Kummer discovered? Well, remember the cyclotomic integers that Euler first observed? It turns out that both Lamé and Cauchy were using these cyclotomic integers and the ensuing interesting factorization of x to the n plus y to the n equals z to the n. How? Well, recall that you can extend the integers with what we call nth roots of unity, the solutions of x to the n equals 1, which we denoted 1, zeta n squared, all the way to zeta n to the n minus 1. With this new extended number system, the formula x to the n plus y to the n can be factorized as such: x plus y times x plus zeta n y times x plus zeta n squared y, all the way to x plus zeta n to the n minus 1 times y. Then, using this fact, they could theoretically use an argument of infinite descent to prove Fermat's last theorem. Just one thing. As you may know, integers can be split into their prime factorizations. Integers are special in that this factorization turns out to be unique, as in, each prime factorization matches exactly one integer, and one integer has exactly one prime factorization. The problem is, Lamé and Cauchy's method relied on the assumption that the cyclotomic integers also enjoyed this unique factorization property. But there was nothing that proved this was the case. Perhaps neither Lamé or Cauchy realized that this assumption could poke an unfixable hole in their proofs. Liouville told Lamé that this assumption should be fixed immediately. Thus, for months after Lamé and Cauchy's announcements of their impending proof of Fermat's last theorem, both mathematicians furiously tried to prove the unique factorization of cyclotomic integers. So you can imagine the devastation when Kummer delivered a letter to Liouville that cyclotomic integers in fact lacked unique factorization. The reason Lamé and Cauchy couldn't prove the unique factorization property was because it wasn't true. This realization hit Lamé quite hard, feeling humiliated that he worked naively upon a dangerous assumption. Cauchy, on the other hand, refused to give up. Perhaps he thought his method relied less on unique factorization than Lamé's, or perhaps Kummer's own proof was incorrect. But soon enough, it was clear that Kummer was correct, and Cauchy had to give up. But Kummer did not just prove Lamé or Cauchy's methods were incorrect. Indeed, while yes, the cyclotomic integers lacked unique factorization, if you could somehow extend this number system just a bit more, perhaps you can make a number system that does have unique factorization. In fact, this is exactly what he found, and he called these numbers ideal numbers. The ideal numbers save the unique factorization for cyclotomic integers, meaning you could then use an approach similar to Lamé and Cauchy to then tackle Fermat. And Kummer showed that yes, you can indeed tackle Fermat, but you couldn't knock it over. Using ideal numbers, he found that you can prove Fermat's last theorem for specific prime values, which he called regular primes. Unfortunately, there are an infinite number of irregular primes. So while Kummer did make significant progress, there was still, frustratingly, an infinite amount of work left. For now, tackling the irregular primes seemed impossible with the mathematical tools of the mid-19th century. However, these irregular primes could be brute forced one by one, something done much later computationally, but in any case, this was seemingly as far as this approach could go. It was perhaps disappointing for these passionate Parisian mathematicians who dreamed of a solution to Fermat in their lifetime. In 1857, Cauchy concluded the past decade of Fermat-related work, stating, quote, "The question remains at the point where M. Kummer left it." However, the mathematical sciences should congratulate themselves for the work which were undertaken by the geometers, with their desire to solve the question, specifically by M. Kummer, and the commissaries think that the Academy would make an honorable and useful decision if, by withdrawing the question from the competition, it would adjugate the medal to Mujur Kumar for his beautiful researches on the complex numbers composed of roots of unity and integers. A moment of humility after a lifetime of both mathematical triumphs and failures. Cauchy died that same year in May at the age of 67. His rival Lame died in May of 1870 at the age of 74, and Kumar in May of 1893 at the age of 83. But that was it. The greatest attempt to tackle Fermat's last theorem so far ended in what seemed like failure. But maybe that's giving too little credit to not only Kumar, Lame, or Cauchy, but all the other mathematicians who were part of this journey so far. Sure, Fermat wasn't solved, far from it, but they showed that Fermat was not invincible, that you could attack it and it could occasionally tip over. Not to mention the burst of novel ideas and techniques that were developed along the way. For now, the mathematicians would stay beaten, but it would take just one new idea to bring them back on the attack. We now go some 100 years after the French Academy of Sciences competition. During these 100 years, mathematics grew and changed in all aspects. New fields, theories, concepts, and ideas formed that made mathematics much richer than just a century ago. But the idea that's relevant to our story wasn't discovered in France or Europe or even the now dominant United States. For our story, we go to Japan, at the University of Tokyo in 1954. Goro Shimura was at the departmental library looking for a book, but it turned out that another student, Yukata Taniyama, had already borrowed the book. After some correspondence, the two became good friends. The duo were born 3 years apart, Taniyama in 1927 and Shimura in 1930. The Second World War had a devastating impact on their access to education, not only with military curriculum and factory work becoming mandatory, but also due to bombings and raids. For Taniyama, his tuberculosis forced him to miss 2 years of high school and eventually graduate later than everyone else. Despite these problems, both Taniyama and Shimura had the passion and the talent to further their mathematical careers. One of the subjects that both mathematicians were interested in was algebraic geometry. Algebraic geometry, in essence, is the connection between geometry and algebra. You may remember graphing lines and parabolas based on polynomial equations in grade school. Algebraic geometry deepens this notion. Now, algebraic geometry is a vast and expansive branch of mathematics like any other, but the key concept for our purposes is what's called an elliptic curve. Elliptic curves, unlike their name suggests, are not curves that look elliptic. Instead, they're a specific type of cubic curves, which are polynomials in 2 variables, we'll call x and y, where the maximum degree is 3. But we have to specify what types of numbers we can use to describe this curve. Recall the concept of the ring, a number system in which you can add, subtract, and multiply. Fields are a type of these rings, with the added requirement that you must also be able to divide. Number systems like the rationals, reals, and complex numbers are some examples of fields. But there are other, weirder fields that act a lot more differently than we're used to, and in these cases the equations for elliptic curves can get a bit complicated. But for the case of the field of rationals and the reals, which are the fields we'll look at the most, we can simplify the equation of an elliptic curve to y squared equals x cubed plus ax plus d. In 1955, an international symposium on algebraic number theory was held in Tokyo. For Taniyama and Shimura, this was the perfect opportunity to show the rest of the mathematical community their ideas and findings. Algebraic number theory, like algebraic geometry, uses algebraic methods to solve problems in number theory. For example, Kumar's work on ideals was a part of algebraic number theory. If Fermat's last theorem were to be solved, many methods and foundational ideas would come from this field. The symposium was attended by Andrew Wiles, a French mathematician who Shimura had corresponded with 2 years prior. Wiles was one of the key speakers at the symposium, with influential work in both algebraic geometry and algebraic number theory. Thus, it's no surprise that Weil had a massive impact on both the work of Taniyama and Shimura. During the symposium, Taniyama posed several questions and problems about elliptic curves. In particular, he hinted that elliptic curves had a deep connection with another mathematical object called modular forms. Modular forms are probably the most abstract and strange concept we'll run into. First, there is the concept of a complex function. We talked a little about complex numbers, but for now, we just think of them as points on 2D space. Then a complex function basically takes these points and moves them to another point in 2D space, as defined by the function. For example, the complex function fz is equal to z squared moves this point here and this point here. In general, you can imagine that the entire plane transforms by these rules. Now, there are some properties of complex functions that we like, and an important one is called holomorphic or analytic. The intuition is that if you have two lines on the plane, intersecting at some angle, the function preserves these angles as the lines are transformed. If you want a bit of formality, then this is kind of like a differentiable function, but for complex functions. So a modular form is a type of holomorphic complex function. It takes inputs not from the entire plane, but just the upper half of the plane. Then for any complex number z in the upper half plane, a modular form should satisfy this equation, where this here is just an element of what's called the modular group, which are just functions related to 2x2 matrices of determinant 1. And there's also a growth condition. And if you're lost, don't worry, I can barely keep up with a lot of this stuff. But honestly, for the purpose of this video, that's fine. You just need to know that modular forms are nice transformations of points on the 2D plane that satisfy some interesting properties. But yeah, its definition is quite abstract and also seems nowhere related to elliptic curves, much less Fermat's last theorem. But it turns out, modular forms are linked with many other mathematical theories and objects across number theory, analysis, and algebra. And this is what Taniyama theorized, that there existed some deep, powerful connection between elliptic curves and modular forms. The idea was that any elliptic curve, E, has a sequence of numbers attached to it. We can call a sub n E for each positive integer n. For every prime number p, APE is related to the number of points on the elliptic curve, that is, the number of solutions xy that we can find for the elliptic curve. Then for any modular form f, we can associate f with something called a Fourier series, which is of the form fq is equal to a1fq plus a2fq squared plus a3fq cubed, and so on. And then we can thus take the coefficients a1f, a2f, a3f, and so on to make a sequence associated with f. We then call an elliptic curve E modular if there exists a modular form f such that APE is equal to APF for almost all primes, or more formally, all but finitely many primes p. The point is, there exists a potential connection between elliptic curves and modular forms, and if we find an elliptic curve that satisfies that connection, we call it modular. And Taniyama's conjecture was that, in fact, every rational elliptic curve was modular. If true, his conjecture could build a bridge between elliptic curves and modular forms, and in turn between number theory and analysis. But it was only a conjecture, and at the time not many mathematicians took particular attention. But not Shimura. Shimura helped his friend Taniyama refine and develop the conjecture for the next 2 years. And during all this, both Taniyama and Shimura's mathematical career began to rise. Shimura was invited to Paris with the help of Weil as a researcher at the National Center for Scientific Research, then spent 7 months at the Institute for Advanced Study at Princeton. Taniyama met a woman named Misako Suzuki in November of 1957 and became engaged soon after. By 1958, Taniyama was also offered a position at the Institute for Advanced Study. Yet, despite his promising future in both life and mathematics, on November 17, 1958, Taniyama committed suicide. He was only 31. Taniyama left a suicide note in which he describes his tiredness both physically and mentally, as well as his loss of confidence for the future. Only a few weeks later, Misako Suzuki also committed suicide, leaving a note that said, "We promised each other that no matter where we went, we would never be separated. Now that he is gone, I must go too in order to join him." Shimura was devastated. He stated that, quote, "He was always kind to his colleagues, especially to his juniors. and he genuinely cared about their welfare. Probably he was never conscious of this role that he was playing, but I feel his noble generosity in this respect even more strongly now than when he was alive, and yet nobody was able to give him any support when he desperately needed it. Reflecting on this, I am overwhelmed by the bitterest grief. Despite the tragedy, Shimura continued the work he and his friends started. By 1967, Weil also built upon Taniyama and Shimura's conjecture and found more evidence supporting it. Weil helped spread the conjecture throughout the West, and soon enough the conjecture seemed more and more likely to be true. And this was great news. Such a deep connection between two branches of mathematics would mean so many new tools, techniques, and ideas to solve problems in both fields. In fact, Taniyama Shimura was so powerful that many mathematicians began assuming the truth of the conjecture and used it to show various results that could arise from it. By the 1970s, numerous mathematical discoveries and statements were based on the validity of the conjecture. That's how powerful and important the conjecture was. And while mathematicians were reveling in the possibilities that Taniyama Shimura gave them, they knew that if the conjecture was proven to be false, all this work could come crashing down. The Taniyama-Shimura conjecture was massive for many areas of mathematics, but it stayed firmly separate from Fermat's last theorem for some time. No one really thought the two problems were connected. Only a whole 20 years after the Taniyama-Shimura conjecture was formed, did some potential links between the conjecture and Fermat's last theorem began to be found. A French mathematician named Yves Hellegrach noted a connection between the equation a to the p plus b to the p equals c to the p for odd primes p and the equation y squared equals x minus a to the p, x plus b to the p. Now, if Fermat's last theorem was false, and there were integer solutions for a, b, and c, then this equation would actually be an elliptic curve over the rationals. But the properties of this so-called elliptic curve were rather odd. In fact, it seemed like this elliptic curve may not even be an actual elliptic curve. If one could perhaps show that such an elliptic curve could not exist, that would mean that the non-trivial solutions for a to the p plus b to the p equals c to the p cannot exist for an odd primes p, which is all we need to prove Fermat's last conjecture. Hellegrach didn't go too far in doing this, but then a German mathematician named Gerhard Frey got the ball rolling. Frey was born in June 1944 at Erlangen, Germany. He received his PhD in 1970 at Heidelberg University, and he eventually became a professor at the University of Erlangen in 1973, and then at Saarland University in 1975. Studying number theory and algebraic geometry, Frey had the knowledge to dig deeper into Fermat's last theorem and the Taniyama-Shimura conjecture. Hellegrach's unusual curve, according to Frey, was not only just unusual, but it seemed to be not modular. In other words, if a solution existed to Fermat's last theorem such that this elliptic curve, which we now call the Frey curve, existed, then it would violate the Taniyama-Shimura conjecture, which says that every elliptic curve is modular. On the other hand, if the Taniyama-Shimura conjecture was true, such that all elliptic curves were indeed modular, then Frey's curve could not exist, meaning a solution to a to the n plus b to the n equals c to the n could not exist. Gerhard Frey presented these findings to a mathematical symposium in 1984 in Oberwolfach, Germany. But the audience and Frey soon realized that there was an error in Frey's reasoning. Frey's method of solving Fermat through Taniyama-Shimura was plausible, but not certain. Whoever could fix this error would put a definitive connection between the two conjectures and provide, for the first time in over a century, a promising new way to tackle Fermat's last theorem. In fact, it seemed that the Taniyama-Shimura conjecture could be the decisive blow to knock out Fermat's last theorem once and for all. The race was on for someone to precisely describe this connection. But months passed after Frey's presentation, and it seemed no one was particularly successful. To be fair, looking at the history, this was no surprise. Every time some new promising method or idea came up with the potential to unlock Fermat's last theorem, there was always some gap, or logical error, or mistake. But in 1985, some progress was finally made. A French mathematician named Jean-Pierre Serre gave a partial proof that the Frey curve was not modular. Serre was born in 1926 at Pyrenees Orientales. Mathematically gifted from a young age, he joined the Bourbaki group in the late 40s, becoming the youngest in the group at the time. The Bourbaki group was an influential group of French mathematicians, which included our old friend Andrew Wiles. They worked under a pseudonym of Nicolas Bourbaki. Serre got his PhD at the University of Paris in 1951 and eventually won a Fields Medal in 1954, the most prestigious award in all of mathematics. He was, and still is, the youngest ever to win the award at just the age of 27. Back to his work on Fermat's Last Theorem, on top of giving a partial proof that the Frey curve was not modular, Serre showed that if the Frey curve was indeed modular, then you'd only need to prove the Taniyama-Shimura conjecture for a specific class of elliptic curves, called semi-stable elliptic curves. But there was a small bit of the foolproof that was missing, called the epsilon conjecture. In mathematics, most frequently in analysis, epsilon represents a very small number. Serre showed that if you can solve this small epsilon conjecture, then you definitively show a connection between Taniyama-Shimura and Fermat. That is, if you proved the Taniyama-Shimura conjecture for semi-stable elliptic curves, then you'd also prove Fermat's last conjecture. Now, all mathematicians needed was this small epsilon conjecture. One of the mathematicians who was tackling this epsilon was Ken Ribet, an American mathematician. Ribet was born in June of 1948 in New York. He got his PhD from Harvard in 1973 and eventually began to teach at UC Berkeley in 1978. Ken Ribet's main work in mathematics was in number theory and algebraic geometry, which, as we discussed, were the fields in which Fermat's last theorem and its potential solution lay. Ribet had already cracked a special case of the epsilon conjecture, and had sent an electronic message to a Harvard colleague named Barry Mazur. Mazur was impressed by Ribet's argument, but unfortunately Ribet could not crack the full case of the epsilon conjecture. In the summer of 1986, mathematicians from all over the world met for the quadrennial International Congress of Mathematicians, and it happened that the location for the event was in Berkeley. Barry Mazur thus came to Berkeley to attend the event and spoke with Ribet about his progress in proving epsilon. For some frustrating reason, Ribet just couldn't connect his argument on the special case to the general case. But Mazur looked at Ribet, confused. Ribet had shown the general case. He only needed to add a small supplemental along with his argument and he'd get the full epsilon conjecture. Of course, it was so simple, so obvious. Well, at least to these brilliant mathematicians. But Ribet verified Mazur's logic and proved epsilon, thus showing that the Frey curve was indeed not modular. Since there were thousands of mathematicians at Berkeley for the ICM, the news of this discovery spread. Now the mathematical community knew for a fact that the Taniyama-Shimura conjecture implied Fermat's last theorem. There was now a concrete way to prove Fermat. But the Taniyama-Shimura conjecture itself was an open problem for over 30 years, and it's not like nobody tried to solve it. Many had already thought the Taniyama-Shimura conjecture was out of bounds for contemporary mathematical techniques. The bridges were built, but crossing them was a whole other challenge. In 1963, a 10-year-old boy named Andrew Wiles was strolling through a local library looking for a book to read. Wiles was young, but already had a fascination for mathematics. On this occasion, Wiles happened upon a book called The Last Problem by Eric Temple Bell. He read about a problem posed by a particular Frenchman from the 17th century. It was a simple problem, one he, a child, could easily understand. A to the n plus b to the n equals c to the n has no positive integer solutions for n greater than 2. He read the extensive history of the problem and the failures that lay on its road. How centuries of the greatest minds could not solve such a simple-looking problem. It was like love at first sight. He wanted to solve this incredible, beautiful, and frustrating problem. Andrew Wiles was born in Cambridge in April 1953. He did his undergraduate studies at Merton College at the University of Oxford in 1971, and then went to Clare College at the University of Cambridge for his doctorate in 1974. His advisor was Australian mathematician John Coates, who recognized the brilliance of Wiles. Now, While solving Fermat's last theorem was a lifelong dream for Wiles, there was no way he would try to solve that during his graduate studies. In fact, only the most bold and daring of the highest level mathematicians would even dare to try and face Fermat at all. For now, Wiles and Coates began to study what's called Iwasawa theory. Iwasawa theory was developed by a Japanese mathematician named Kenkichi Iwasawa. It concerns what are called infinite towers of number fields. Do you remember the cyclotomic integers we talked about a long time ago? You know, the extension of the integers used by Lame, Cauchy, and Krummer to tackle Fermat's last theorem? Iwasawa theory used these ideas to build essentially an infinite line of extensions of the rationals. It's a rich and interesting concept in number theory which my brief summary cannot suffice. But while Iwasawa theory shares some common ground with the history of Fermat's last theorem, that was about as much relevance that Iwasawa theory had on Fermat's last theorem. At least, for now. Because Wiles and Coates weren't just studying Iwasawa theory, they were using the methods of Iwasawa theory to solve problems about, well, elliptic curves. And remember, it's still the 1970s and Fry's lecture connecting Fermat's last theorem to elliptic curves wouldn't happen until 1984. So as far as Wiles knew, he wasn't really doing anything related to Fermat. For him, he had to work on other more relevant and accessible mathematics, and maybe, in the future, he could be fortunate enough to spend some time on his childhood dream. Wiles and Coates' partnership proved fruitful, and Wiles earned his PhD in 1980, becoming a professor at Princeton in 1981. Around this time, he also worked with Barry Mazur to prove an important theorem in Iwasawa theory based on some previous work of Ken Ribet. This work specifically has nothing to do with Fermat's last theorem. I just find it amusing that these three mathematicians were first connected outside of our story about Fermat. The year that Wiles and Mazur proved their theorem about Iwasawa theory, Fry gave his lecture on Fry curves, and 2 years later, Ken Ribet would tie the knot in proving that the Taniyama-Shimura conjecture would imply Fermat's last theorem. It was that summer of 1986 that Wiles heard the news. This was it. He could actually work on Fermat's last theorem. He had experience with elliptic curves, and while the learning curve to actually try and solve the Taniyama-Shimura conjecture was steep, he was now given a clear path to potentially solve Fermat. At that moment, he would abandon all other research and put his sole focus on cracking the Taniyama-Shimura conjecture. And he would do so for 7 years. Wiles worked in total secrecy. The only other person who knew of Wiles' work was his wife. There were a number of reasons that Wiles worked in total secrecy. While the recent breakthroughs regarding the connections between Fermat and Taniyama-Shimura were huge, the problem was still immensely difficult and thought to be inaccessible by many. Thus, working on the problem may have garnered negative attention from many who considered it futile. Now, the word hype isn't one usually applied to academia, but if it was, Fermat's last theorem during this time would have been the appropriate place to use it. There was a lot of interest, and the number of spectators and eyes watching a prolific mathematician like Wiles working on such a big problem would certainly distract him from his work. And perhaps another reason was for the glory. Wiles was going for something huge, arguably the biggest mathematical problem in history, and he was about to put years upon years into his work. He knew the progress of the problem would be slow, and if he revealed his process throughout the years, there was a good chance that someone else could snatch the proof before he did. But still, to work in complete secrecy and isolation was quite unheard of. Collaboration is one of the biggest factors in the growth of mathematics. I mean, look at all the names that appear throughout this video. It's exponentially difficult to walk the road of solitude in mathematics. But this didn't faze Wiles. He loved doing what he did, actively solving a problem he wanted to solve since he was a boy. But what was Wiles' work like? Well, I for one am nowhere near qualified to understand the vast majority of Wiles' proof, but I can provide a brief summary of the general ideas and steps that Wiles takes. Wiles employs a very common tactic of proof called proof by contradiction. This is the same proof technique that the argument of infinite descent employs all the way back from Fermat himself. In Wiles' case, he assumed that Fermat's last theorem was false, meaning that there exists positive integer solutions for a to the n plus b to the n equals c to the n where n is greater than 2. Then, as we discussed previously, this implies the existence of the Fry curve, an elliptic curve which, thanks to work of Serre and Ribet, we know is semi-stable and cannot be modular. But the Taniyama-Shimura conjecture says that all elliptic curves are modular. So if Wiles proves the Taniyama-Shimura conjecture for semi-stable elliptic curves, then we have a contradiction. So Fermat's last theorem must be true. Okay, so how do you prove Taniyama-Shimura for semi-stable elliptic curves? Wiles used what are called Galois representations of elliptic curves. If you remember, we talked about number systems called fields. Just as Lamé, Cauchy, and Kummer extended the integers to cyclotomic integers, you can extend fields to what are called field extensions. A French mathematician from the early 19th century named Évariste Galois worked with these field extensions and functions between field extensions. A special kind of function called automorphisms of a field extension can be represented by structures called Galois groups. This idea turned out to be immensely powerful in describing many concepts in algebra, and this Galois birthed a whole theory in mathematics called Galois theory. For Wiles' proof, Galois representations use the ideas of Galois theory and Galois groups to represent elliptic curves. Now this is important because establishing a direct connection between elliptic curves and modular forms is not easy. It's much better to use these Galois representations to, well, represent corresponding elliptic curves. Now these Galois representations of elliptic curves also have the property of being modular. So the idea was to show that if the Galois representation of an elliptic curve is modular, then so is the elliptic curve itself. If you could show this connection, then working with elliptic curves would be a lot more easier. But then less than 2 years into Wiles' work on Fermat, in March 1988, he woke up to some devastating news. Fermat's last theorem had been solved by a Japanese mathematician named Yoichi Miyaoka. This was especially surprising news for Wiles, who believed that no one else would really be attempting Fermat as well. After all, despite the recent hype around Frey, Serre, and Ribet's work, the Taniyama-Shimura conjecture was incredibly difficult to even approach, and Wiles was only one of the few mathematicians who had the deep knowledge on elliptic curves and other theories necessary to even attempt the problem. But Miyaoka didn't use elliptic curves or the Taniyama-Shimura conjecture. He used a related but different branch of mathematics called differential geometry, the study of geometric shapes and surfaces. Since the 1970s, mathematicians have attempted to connect ideas and problems in differential geometry and number theory in what became arithmetic algebraic geometry. One crowning achievement in this department came in 1983, when German mathematician Gerhard Faltings studied the surfaces created by the equation of Fermat's last theorem. Using the methods of arithmetic algebraic geometry, he showed that there could only be a finite number of solutions for a to the n plus b to the n equals c to the n for n greater than 2. This could be a billion, trillion, maybe 12, or maybe 0 solutions, the latter of which is the conjecture that Fermat proposed. This advancement, as well as the general theorem he used to prove it called the Mordell conjecture, landed Faltings a Fields Medal in 1986 at Berkeley, where our good friend Barry Mazur gave an address describing Faltings' work. Remember, it was here in Berkeley at this time that Ribet, with the help of Mazur, proved the connection between Taniyama-Shimura and Fermat. But as impressive as Faltings' methods were in tackling Fermat's last theorem, it didn't seem like it could extend to solving the full conjecture. Well, until Miyaoka arrived. He announced the outline of his proof in 1988 at the Max Planck Institute of Mathematics in Bonn, Germany, showing that he had extended Faltings' method to cover the whole of Fermat's last theorem. For the audience, Miyaoka's ideas were very exciting. Many felt that this could genuinely be the path to solving Fermat's last conjecture. 2 weeks after his seminar at Bonn, Miyaoka released his proof, but only a few days later, a contradiction seemed to appear. An additional 2 weeks later, Faltings realized why. There was an error, a gap in the proof. Just like all the mathematicians before him, there was a key error that prevented Miyaoka from a correct full proof. While many other mathematicians tried to patch the gap, it soon became clear that Miyaoka's method could not work. Of course, this was not all for nothing. Miyaoka had still discovered novel ideas and techniques that bridged geometry and number theory, just like how Fermat, Lamé, Cauchy, and Kummer created an abundance of mathematical advancement on their failed road to Fermat. But in the end, it was history repeating itself. Fermat was still unbreakable. For Wiles, it was perhaps a relief that he could continue working on Fermat, but also a warning that, indeed, the task he was trying to achieve was far from easy. he had to make sure his logic was airtight, or he might just end up among the names which paved the road to Fermat, but never reached its destination. By 1990, around 4 years since Wiles began his work, Wiles became stuck. As we mentioned previously, Wiles wanted to show that if a Galois representation of an elliptic curve is modular, then so is the elliptic curve itself. Now, this wasn't an easy task. There are an infinite number of elliptic curves, each with an infinite number of pieces. Now, a powerful way to go through an infinite number of problems in mathematics is to use a method called induction. It's the mathematical equivalent of setting up dominoes. In essence, you show that if something is true for one of your objects in your infinite line of objects, then it must be true for the immediate next object. In this way, we set up a line of dominoes where if one domino falls, then each successive domino falls as well. Then we show that something is true for the first object, which is like toppling the very first domino. If all the dominoes are set up properly, then they all fall in a neat, orderly line. With this method of induction, a carefully crafted proof can solve infinite problems in one swoop. To achieve this, Wiles first began by using concepts from Iwasawa theory, but even this method was not enough. By 1991, Wiles began to look for other potential approaches to the problem, and the answer came from none other than his former advisor, John Coates. He pointed Wiles towards a recent new development regarding elliptic curves by Matthias Flach, who built upon the work of Victor Kolyvagin on something called Euler systems. Again, going past the immense technical details, these techniques from Kolyvagin-Flach could potentially solve his induction argument. Using Kolyvagin-Flach, Wiles succeeded in showing that, with a few conditions, if the Galois representation of a semi-stable elliptic curve was modular, then so was the elliptic curve itself. This was a massive step in Wiles' proof, called the modularity lifting theorem, and from here, the rest of the proof just began to fall into place. You see, Galois representations of an elliptic curve also depend on a prime number related to the number system which the elliptic curve is being described over. But Wiles' theorem states that if you show a Galois representation is modular for any prime, then so is the elliptic curve itself. So depending on which elliptic curve you're working with, you can switch between different prime numbers to more easily solve the problem. For Wiles, the case of p equals 3 was particularly useful, especially because there were existing results of Galois representations relating to the p equals 3 case. There were specific instances in which p equals 5 was easier to use, and thanks to the power of the modularity lifting theorem, this 3-5 switch was able to cover the case of all semi-stable elliptic curves. In the final stages of his proof, around January 1993, Wiles employed the help of a fellow colleague named Nick Katz to help in making sure his work on Kolyvagin-Flach was operating smoothly. You see, Kolyvagin-Flach was still a very new and very difficult piece of mathematics, and Wiles had to make sure that there was no gaps or errors in his utilization. Katz was surprised to see that his friend had been secretly working on Fermat for the past 7 years, then agreed to help Wiles in checking his work. And it seemed to the two that everything fell into place. It was one afternoon in May of 1993. Wiles' wife, Nada Kanan, was waiting for her husband to come down to eat lunch. After a while, Wiles finally descended from his attic. Nada was surprised to see Wiles not only so late, but with such an excited look on his face. Then, Wiles told his wife, "I've solved Fermat's last theorem." Wiles decided to announce this momentous occasion in June at a conference in Cambridge. Mind you, at this point, only a very small number of mathematicians actually knew that Wiles was working on Fermat, much less that he'd proved the whole thing. Rumors began circulating about the exact nature of Wiles' lectures. Wiles seemed to have wanted a bit of a spectacle as he had not clearly disclosed the enormity of the discoveries. Wiles' lecture would span 3 days. The first day did not particularly reveal too much, but the rumors would continue to spread. The audience for day 2 was much larger, and this time, Wiles showed parts of his argument to Tako Taniyama Shimura. Not enough for the audience to conclude that he'd solved it, but enough to crescendo their expectations for the third day. By day 3, the auditorium was overflowing with mathematicians. Practically everyone was there: Barry Mazur, Ken Ribbett, John Coates, Victor Kolyvagin, all the names whose work would culminate in this moment. As Wiles conducted his lecture, laying out his incredible, brilliant work that he dedicated his life to over the past 7 years, everyone in the room did not doubt the conclusion. Wiles read out the proof, then simply wrote Fermat's Last Theorem. "I think I'll stop here," he said, and the room erupted into applause. It might seem odd to most people that some mathematical lecture would warrant such passion and excitement, but if you've watched until now, you know why. This problem had been one of the most prized and the most difficult for centuries. Such a simple problem, yet so frustratingly difficult to crack. It was historic. One of the greatest problems ever to be solved in the history of mathematics. This was a victory not just for Wiles, but the entire mathematical community. And even the media knew about the monumentality of this event. News outlets, TV stations, and constant interviews flooded all those involved. Of course, the proof now had to go through review. A number of referees were hired to examine the over 100 pages of dense, innovative mathematics. Due to the sheer size and importance of the paper, it was divided into 6 chapters, which 6 referees would each review. Nick Katz, one of Wiles' only correspondents during his 7 years of work, was chosen to referee Chapter 3. When something confusing or seemingly flawed arose, Katz would promptly email Wiles and they'd get it sorted relatively quickly. Most of these problems were like grammatical errors and could be smoothed out with not much fuss. On August 23rd, Katz emailed Wiles about another seemingly minor issue. Wiles gave his response, but it didn't really answer Katz's question. So after another email from Katz, Wiles sent another response. Katz continued to bother Wiles about this problem, and eventually, Wiles realized that this problem was not as simple as all the others. In fact, it was a fundamental flaw. There was something wrong with Wiles' implementation of Kolyvagin-Flack that would poke a gaping hole in Wiles' proof. This was devastating news. Wiles decided he'd try to fix the gap before telling the rest of the mathematical community that Fermat wasn't yet resolved. He returned to isolating himself and focused on fixing this problem. But as time passed, the problem would remain frustratingly out of reach. And now, Wiles was working under the pressure of time. You see, the paper was not yet distributed to the wider community, and mathematicians were beginning to ask questions on the progress of checking the proof. Rumors began circulating that Wiles' proof has a gap. Eventually, Wiles had to give in. In December, Wiles announced that there was a gap in the proof. Wiles stated that he believed he would be able to fix this gap soon, but I don't think anyone, including Wiles himself, really believed this statement. It was a nightmare for Wiles. Remember, there's a reason he worked in complete isolation. He disliked the noise and attention on working on a problem like Fermat. You can imagine then the pressure that he felt as every mathematician in the world, and even the general public, was looking at his every action. And honestly, who could blame them? Fermat was not only one of the biggest problems in mathematics, but it was notorious for his failed proof attempts. Wiles eventually decided to rely on another mathematician for help. His name was Richard Taylor, who was one of the referees and Wiles' former student. But even with his help, progress seemed non-existent. Then suddenly, the following email popped up in April of 1994. A mathematician named Andrew Wiles claimed that Noam Elkies found a counterexample to Fermat's last theorem. In other words, he had actually found a set of positive integers which satisfied the equation. The reason Wiles couldn't complete the proof was because there was no proof. Fermat's last theorem was incorrect. Not only that, this also meant that Taniyama-Shimura was incorrect, as this solution implied an elliptic curve which was not modular. Remember, a multitude of mathematics relied heavily on the assumption that Taniyama-Shimura was true. This was truly devastating news. Except if you look closely at the date, it was just an April Fool's prank. Henri Darmon was committing a bit of tomfoolery. For now, the validity of Fermat still firmly rested on the hands of Wiles and Taylor. It was now September, around a year since the error was first discovered. Wiles was on the verge of giving up. He had held on for as long as he could, but the pressure was just too much to bear. It was only right to release his paper to the public so that at least others could fix the error. Of course, this meant that the full glory of solving Fermat was not truly his. But what could he do? He had tried everything.
In September, I decided to go back and look one more time at the original structure of Flack and Kolyvagin to try and pinpoint exactly why it wasn't working. Totally unexpectedly, I had this incredible revelation. I realized what was holding me up was exactly what would resolve the problem I'd had in my Iwasawa theory attempt 3 years earlier. It was the most important moment of my working life. It was so indescribably beautiful. It was so simple and so elegant. And I just stared in disbelief for 20 minutes. Then during the day I walked around the department. I'd keep coming back to my desk and looking to see it was still there. It was still there. The first night I went back and slept on it. I checked through it again the next morning, and about 11 o'clock I was satisfied, and I went down, told my wife, I've got it, I think I've got it, I found it. And it was so unexpected. I think she thought I was talking about a children's toy or something. I said, got what? And I said, I fixed my proof, I've got it.
He'd done it. The greatest mathematics problem of all time solved. Wiles submitted his final 109-page proof of Fermat, along with a supplemental paper written with Richard Taylor to fix the gap. This time, there was no drama, no anticipation, no final turns. It was done. The proof was verified, and the mathematics community celebrated an incredible milestone. For Wiles, it wasn't easy. It was probably the most stress-filled, painful year of his life. But he had achieved something he wanted to since he was a little boy. He solved Fermat's last theorem. This problem looks simple at first sight. Even a middle school student can understand the statement of the theorem. But it took hundreds of years, a significant number of mathematicians, and cutting-edge mathematics to finally topple the problem. And the thing is, after Fermat was solved, that was it. I mean, don't get me wrong, the innovative methods used and expanded upon by Wiles, and the validity of Taniyama Shimura and so forth, had their own important implications in mathematics. But the actual statement of Fermat's last theorem was nothing more than another checkmark in a big list of unsolved problems from bygone era. You may wonder why so many mathematicians worked on such an inconsequential problem. It doesn't solve any real-life problems. It doesn't benefit humanity in any tangible way. But you know the answer. We met so many different mathematicians from different backgrounds and across hundreds of years. But the one thing they all had, the one unifying property, was their love and passion and curiosity. And this is just one story, one small theorem in the vast and long world of mathematics. Fermat's last theorem is probably one of the most recent big problems solved in mathematics, along with perhaps the Poincare conjecture. Currently, there are a huge number of problems which are unresolved and thought to be out of reach by modern-day mathematics. The Millennium Prize problems, which are important mathematical problems with million-dollar bounties, definitely make this list. But there are many like Fermat's last theorem, which sound simple and elementary in their statement, but have resisted the force of mathematics for centuries. Problems like the twin prime conjecture, Goldbach's conjecture, the Collatz conjecture, the existence of odd perfect numbers, and so on are some famous examples. But who knows? Maybe there's another Andrew Wiles out there somewhere, putting together a beautiful proof after years of solitude. Perhaps we're waiting for a Fry, Serre, and Ribbit to find incredible connections between existing problems. Perhaps we're awaiting brilliant minds like Taniyama and Shimura to discover a new revolutionary idea that will change mathematics as we know it. Or perhaps we are like Germain, Lamy, Cauchy, Kummer, learning even in our failures. Or perhaps, just maybe, we're waiting for a Fermat who will propose a brilliant, simple, and insanely difficult problem that would challenge mathematics as we know it. Who knows? But looking back at the wonderful story of Fermat's last theorem, I don't doubt that our curiosity will never give up looking for new problems, new methods, new solutions. Until next time.